Hey everyone, Dr. B here. Pardon me for taking so long to post this video, but it's just been a really busy past 2 weeks. So hopefully this will help you out for those that haven't finished their project yet. Um, so let's go ahead and go through the assignment. I went through it in class, but remember that everything has to be typed. A template has been provided uh, for your solution, right? Initially, you're giving a ordinary differential equation that describes the pitch angle of an aircraft, right? And where SID are the last two digits of your student ID, right? Now, the solution that I developed uses a 00 as SID. I checked the roster, and nobody's student ID ends in 00. So remember that because of this, everybody's going to have a different answer. Okay, so which is a good thing. So, all right. Given that ordinary differential equation, you have your initial conditions. All right, initial pitch is 0, and because of a wind gust, you have a rate of 0.01 radians per second. So it says use Laplace transform residue theorem to find an equation for theta t. Right. This is just like exam one. Now, once you get a solution for theta t, theta is a function of time. Go ahead and plot the result for a time period between 0 and 2 seconds. Okay. You can use the linspace command to generate a time vector between 0 and 2 seconds. All right. And then from there, you can calculate your pitch angle theta t based on that time vector. Now, it says here determine approximately how long it will take for the pitch angle to reach pi over 2 radians. Right? There's several ways that you can do this. I'm going to go to MATLAB here, and so when SID is equal to 0, the solution for theta t becomes 0.001 times exponential function raised to the 4t minus exponential raised to the minus 6t. All right. Now, what you can do to calculate when the angle will equal pi over 2 radians is you can create an anonymous function. All right. Like I said, there's several ways to do it. You could use an interpolation, but I went ahead and used an anonymous function. So, for example, an anonymous function is the result set equal to 0. So, if you define a variable f, right? Actually, let me go ahead and make the font size a little bit bigger so everybody can see it here. Actually, don't know why I'm using such a small font size here at home. All right, so we have f, all right, is equal to at t. So this is saying that whatever function I'm going to type in the parentheses I just opened is going to be a function of t. Now, as I said, theta t, when you let SID equal 0, the solution is 0.001 times exponential function uh, raised to the 4t power minus exp exponential function raised to the minus 6t power, right? And close parentheses. And we want that to equal pi over 2. We want to find out when t equals pi over 2. Now, um, we're going to be using the f0 function to determine this value, which means that we need to set the entire equation equal to 0. So if this equation equals pi over 2, all right, then the equation minus pi over 2 should equal 0. So we say minus pi divided by 2. And you have what's called an anonymous function. And in this case, it's telling you it's a function of time. That's why the t is in parentheses. Right. Then we can determine that time when the pitch angle equals pi over 2 using the f0 function, right? The f0 function requires minimum two inputs. The first input should be, what equation are you solving? Well, we stored that equation under the variable f, the anonymous function. And then you need an initial guess. Based on that initial guess can be determined from the graph that you have to generate for this pitch angle as a function of time. For my graph, I determined that a good guess would be 1.838. Right? And go ahead and press enter. And that would be the time where pitch angle would equal pi over 2 radian. Right? There were uh, there was a couple of people that said that the pitch angle equaled pi over 2 radians after 2 seconds. Go ahead and double check your work. If that's the result you get, that's the result you get. Unfortunately, I cannot check your work for this project. All right, I can only give you pointers like I'm doing here. Right, so that's one way to quickly determine your your time when pitch angle equals pi over 2. Now we go back to our project. All right, we've determined our time when pitch angle equals pi over 2. Right, now it gives you an equation for torque produced. Right, and the error, pitch angle error, which is a function of your desired pitch angle, the actual pitch angle, and the noise. Mm. And then a differential equation for the servo system, all right, which is a function of phi. Go ahead and just call that phi, assuming small angles, all right, and a function of error. So you have four equations, four unknowns, right? So first scenario, assuming the desired pitch angle is 0 and the noise is 0, the initial pitch rate is 0.01 due to a gust, and initial pitch is 0. Go ahead and Laplace transform each of the four equations and eliminate three of the unknowns to get an equation for theta s. Okay? So it becomes once you calculate your Laplace transform, it becomes an algebra problem. Right now, when you Laplace transform this equation 4 here, you assume that your phi 0 and your e 0 are 0. So you assume zero condition, right? Same thing here. When you Laplace transform both sides of this equation, theta d equals 0, n equals 0. So you end up with e equals minus theta. Laplace transform both sides. That should be pretty straightforward. Right? Same thing with your torque, right? And you end up with an equation, capital theta s, which is Laplace transform of your pitch angle. By the way, if you hear pauses, I haven't slept in a while, so I've been a little busy. But so please bear with me. Now it says here to go ahead and calculate your damping ratio, damp natural frequency, and the time constant. All right. One way to do that, again, I'm going to show you the result for SID equals 0, 0. You end up with a denominator in the transfer function, right, which is equal to 1, 53. So you have an s cubed plus 53 s squared plus 269.25 plus s plus 688.5. Okay. So one way to calculate all those things, uh, damp natural frequency, your damping ratios, and your poles. is by using the damp function. All right, so let's have an output damp natural frequency. I'll just go ahead and call it DNF, DR damping ratio, and P for poles is equal to damp, right, D. And you're going to get an output. Notice your damp natural frequencies, your damping ratios, and your poles. Now, when SID equals 0, 0, you have a complex pole, two complex poles, and a real pole, which is negative, which implies exponential decay. Right? So this system is going to be damped down to 0 eventually, this stabilized system, right? Um, your time constants, you can calculate tau, right? Just saying one period divide. Period means go ahead and divide by each number in the pole vector, right? So absolute value, real portion of the pole, all right? That's your R value that we've been working with throughout semester. And those are your uh, time constant. Your simulation time, right, would equal 5 times the smallest, or excuse me, the largest time constant. So, right, you have max tau, right? So that would be your simulation time. Now, the numerator of that transfer function for theta s, when you work out all the algebra, would be these coefficients here. All right. So you have a numerator and denominator, and we can create a transfer function using TF and comma D, the way we did during the semester, right? And it gives you the transfer function for theta s. Now remember, this is for SID equals 0, 0. Okay. From there, we can use the impulse command, right, to generate an impulse plot of the stabilized system. So the x-axis will be time, and the y-axis initially is a magnitude, but you can replace it using y label to theta in radians. All right, so if we press enter, impulse h, you have the system response where the y-axis is in radians. And notice that the response, now that you've added a controller, the response goes back down to 0 after that wind gust. And this is what it means when it says pretend um, theta s of 10 part g is a transfer function with a unit impulse, right? And use the impulse command to obtain a plot of theta t, right? So we generate our transfer function and say impulse of that transfer function. Okay. Now, after that, you can also use that plot to determine how long it will take for the control system to bring the pitch angle back to 0. All right. So now, assuming, and a few people are missing this, assuming all initial conditions are 0 and the sensor noise is 0, all right, obtain a transfer function relating theta s to the desired pitch angle theta d. So you use the same equations that you used above, but in this case, you assume that your initial pitch rate is 0, not just the initial pitch. And a few people were missing that. All right. So assuming all initial conditions are 0 and the sensor noise is 0, you're going to get you should be able to get a really nice expression. All right. So for that transfer function, G of S. Okay. And the last step for this part of the project is supposed to pilot introduces step input 0.1 radians, right? A step input for a desired pitch angle. And it says use the step command to obtain the resulting plot for theta t. Comment on the quality of the step response and so on. All right, so use the step command, and the step input is 0.1 radians. So going back to MATLAB, let me go back to the command window, right? The transfer function that I generated, once again, SID equals 0, 0, right? So it has a numerator, right? The numerator would be 191.25s, right, plus 1912.5, right? That would be the numerator. Denominator, right, would be 1, comma 53, comma 269.25, comma and 688.5. From there, we can generate a transfer function using TF, numerator, denominator. And here's our transfer function relating pitch angle to the desired pitch from the pilot input. All right, and if we go back to the assignment, it says, suppose the pilot introduces step input of 0.1 radian. So analyze this using the step function. Simply, what you're doing is use the step function, as the project asks for, and you multiply that transfer function by 0.1. That's your step input, right? And it's going to generate the step response. So this would be the response that you would get if the pilot gives a step input of 0.1. So that would be the step plot of stabilized system with 0.1 radian pilot input. The X label would be time in seconds. The Y label, it says amplitude. You can change it to theta. That's the actual pitch angle in radians. So hopefully this is a little bit clear. Close this. Right, now let's go back to assignment. That would be the last part for scenario 1. Now we go to scenario 2. Right, assume the desired pitch angle from the pilot is theta d equals 0. Right, initial pitch rate, right, it's equal to this value. Um, it looks like this is a typo. All right, this value right here should be a 0. Otherwise, you're going to get a really weird result. Right. But in this case, assume that the sensor noise n is not 0. So Laplace transform the equation, solve for the transfer function, very similar to the previous process where you had a pilot input and no noise. But in this case, you have no pilot input and you do have noise. So you're going to get a very similar transfer function as you did in scenario 1. Okay. So, right, then it says to assume the transfer function for HS is given by this expression. All right. You can use Bodhi, all right, to verify the bandwidth of the transfer function, that it's approximately 23 radians per second. So let's go back to MATLAB. The transfer function has been given. Let me go ahead and clear this. We can define the numerator again of that transfer function. All right, that would be 38.25. All right, and then 382.5. Right, and the denominator, all right, would equal 0.05, 2.65, and then 42.15, and 321.3. Center. And remember this is the numerator and denominator of this transfer function. Okay. we can create a transfer function, symbolic transfer function using TF again, numerator, denominator. Okay. Now, in order to make that verification of frequency, we need to calculate the target gain. All right. So the first thing we need to do is calculate the DC gain of this transfer function. And remember, that's basically when setting S equal to 0. Fortunately, there's a function in MATLAB called DC gain, all right, which will give you this value here. Right. Now, this DC gain needs to be converted to decibels. And from earlier in the semester, the equation for decibels, 20 times log base 10 of the DC gain. All right. Now, your target, all right, DC gain, let's see here. DC gain would be this value that you calculated. Let me call this target, right? Would be DC gain in decibels, all right, minus 3, as it's explained in the project. So basically, when you create a Bodhi plot, you're going to be looking for this magnitude and at what frequency it occurs. All right. Now, some people are having problems with actually finding the actual value. Let me show you what I mean. So we use Bodhi H, right, to generate the Bodhi plot, right? And we're looking for a magnitude of minus 1.49, for example. All right. So minus 1.49, we can use data tips. All right, click on the curve, minus 1.49. We can drag it. All right. And notice in this case, you have a magnitude of minus 0.7, then it skips to minus 2.45. All right. So it skips from frequency of 25 radians per second to 21.4 radians per second. All right. We don't have a value. The default Bodhi plot doesn't give you a value that's close to minus 1.4849, right? So one way to remedy this is to add more points to the Bodhi plot, right? So let me just initiate a variable called points, right? And this is going to be an array in intervals of zero point 0.1 radians per second, or 0.01, 0.1 like this. And let's go ahead and go to 100 radians per second. All right, so this is going to give you an array from 0 to 100 in intervals of 0.01. So you'll have 0, 0.01, 0.02, and so on, all the way up to 100. Right? Now, let's regenerate our Bodhi plot. We have our transfer function, and the second input would be points. Press enter. Notice you have a more refined Bodhi plot. Right? And we look for that negative negative 1.49. Let's use that, negative 1.49, right? 1.49, negative 1.49. Notice it's this target value that we calculate, all right, rounded to 2 decimals, okay? So we have our Bodhi plot, and notice that that target value occurs at a frequency of 23 radians per second. Okay, if you heard a small pause, had some problems with the microphone. Hopefully, I got this fixed. Okay, So, um, so after a Bodhi plot, you have you want to generate a band limited white noise with one-sided spectral density, right? So I ended up using a value of 5 times 10 to the minus 5 for frequencies between FL and FH. Now there's two sets of frequencies, 1 to 3 and 4 to 6, and I'll go over that in a minute, right? So the objective of this portion assignment is to demonstrate the significance of white noise with frequencies within the bandwidth and noise with frequencies exceeding the bandwidth. That is, noise with frequencies exceeding the bandwidth should be essentially filtered out, right? Um, so right here, I went ahead and I'm going to go ahead and show you what the code should look like in order to generate the necessary plots. Okay, so and it's okay. You can go ahead and copy this from the video, this code right here. You have your bandwidth, which is the 23 degree, or excuse me, 23 radian per second bandwidth divided by 2 pi. That would be your F max. And then your delta F is basically your power spectral density frequency band divided by 100 points. Right? And it's okay to use these values for your project. Now, the given transfer function numerator, here are the coefficients, right? And that's back to this transfer function that was given here. And then you have your denominator coefficients, and then you can generate the given transfer function, right? Now, this is the denominator of the stabilized uh, pitch angle equation, all right, which we used earlier. And as I mentioned earlier in the video, you can calculate the damp natural frequencies, damping ratios, and the poles. We're going to be using the time constants, all right, and then to calculate maximum time constant, magnitude of the poles, PSD time increment, right, and then PSD time increment update. Now, some of you are probably wondering where did all this come from. Well, as the project mentions, right, it comes from this is the assignment. It comes from the book, section 8.3.5.1, right, generating a random time series with a specified input PSD for the simulation, right? And it gives you the entire algorithm that should be used, and that's what I'm going to be showing you in MATLAB, right? So when it says to explain the process is explained right here, right, in this section of the book. So going back to MATLAB, actually, let me get rid of this Bodhi plot. Right, going back to MATLAB, right, we continue with the algorithm, right, and we calculate the H for power spectral density, right. Like I said, it's okay to use this code, right, for your project, okay. Now, based on the values, when we let SID equal 0, we end up with an H of 0.002, frequency bandwidth, n equals 25,000. However, n needs to be a factor of 2. All right, so the next value of n that's a factor of 2, or that's a power of 2, would be 32,768. And that's what the rest of these lines of code are doing. They're making sure that your final n is a power of 2, or 2 raised to some power. Okay, so go ahead and just use this code here. All right, pause the video so you can type it up in MATLAB. Right, eventually you're going to get a final n and a final h, which are the inputs that you need for the stochastic input file that was provided for you on Canvas. All right. Now, here's where we're going to make some adjustments to the stochastic input file. All right. So if you go ahead and open stock input, all right, it's a pretty interesting code. All right, it has fast Fourier transforms and so on. Okay. So what I recommend is that you change the function name twice. The first one, um, you're going to go ahead and save it as stock input F13. So this corresponds to the frequency band between 1 hertz and 3 hertz. Right. So just add to stock input, add F13, and resave it as stock input F13. Right. And you can see right here, I resaved it as stock input F13. And then there's going to be a second one, stock input 46. Okay. So F13. And then two more changes need to be made. Right? Scroll down all the way to the bottom. There is a plot starting on line 61. Right? Go ahead and comment out everything from line 61 to line 68. We don't need that plot. Lastly, you're going to see some code, right? A function gy equals dpsdf, all right? And then you have, it says you need equations or logic for gy describing the desired power spectral density, PSD, right? So for the case between 1 hertz and 3 hertz, go ahead and replace that code at the very end of the function gy equals dpsdf, right? Replace this code right here with this code right here, all right? Now notice this is the value, one-sided spectral density, right? So if we go back to the project, right, that value should be equal to SID, your last two digits of your student number, times 10 to the minus 5. All right. In this case, I'm using 5 because I'm using SID equals 0, 0. Okay. And that's where that value goes. Then you have your lower bound frequency, 1 hertz, upper bound frequency, 3 hertz. And you have a conditional. If your frequency is less than F1, your density is 0. And if your frequency is greater than F2, your density is 0. Basically, it's a filter filtering everything out that's below 1 and greater than 3. So like I said, feel free to copy this code, right? Uh, and make sure that you use the correct one-sided spectral density based on your student ID. Right? You would do the same thing, all right, for the case when frequency range is between 4 and 6. All right, so go ahead and recommend you resave it. All right, resave it as stock input F46. So change the function name and then resave it as F46. And then go to the bottom. All right, make sure you comment out the code, the plotting code, line 61 to 68. And once again, you can copy and paste the code from F13. All right, just copy and paste the code within this function gy dpsd. All right, but make sure you adjust your lower bound to 4 hertz and your upper bound to 6 hertz. This is for the second case. Okay, going back to your noise analysis. All right, once you generate N and H, you can generate noise input in the bandwidth of 1 to 3 hertz. Right, and another noise input, right, in the bandwidth of 4 to 6 hertz. Okay, notice how I'm using the two different files that I saved, that I resaved with different names. The outputs will be a time vector and a noise vector, right, which can be inserted into the LSIM function. That's an L sim. The three inputs, right, would be your transfer function, your noise input, and your time vector, right? And this shows how theta varies with noise 1. And then you can calculate how theta varies with noise 2. So out N1 and out N2. And this is what you're going to be plotting, right? These will be the final plots you should submit for your um, project. All right. So I gave you an example here. You have your time vector and your out N1, and then your second time vector and your out N2. So I'm going to go ahead and run this. All right. And you have theta output with noise 4 to 6 hertz, frequency range, and this is the noise between 1 and 3 hertz frequency range. Okay. All right. Let's close this down. All right. And in your project, all right, it's asking you to calculate your standard deviation and your mean values of your outputs. All right. So, all right, standard deviation is simply STD, right, out N1. So that'd be the standard deviation for your output for the range between 1 and 3 hertz. And then the standard deviation for the output between 4 hertz and 6 hertz. You can do the same, calculate the average, right? All right, for each one of those outputs. Okay. And to calculate the difference or the percent difference between the two, you can use your standard percent difference. Let me call it, just call it PD, percent difference, right? Would equal STD, uh, STD out N1, right, minus STD out N2, okay, divided by STD, STD out N2, all right, times 100. Right, let me maximize this window here. And you would like the absolute value of that entire quantity. Okay. So, hope this helps out with your project. I will be in class on Monday. It was decided that quick update on your exams. It was decided that each professor is going to grade their own section. I have started grading the problems that had not been graded, problems 1 and 3. I originally was in charge of grading problem 2. I am going to try my best to have them ready by class tomorrow, but that might be a little unrealistic. For sure, I will have them ready by Tuesday. And even though our last day of class is Monday, I'll let you know once the grades have been posted on Canvas, and I'll have the exams in my office. And you're welcome to come and pick up your exam during office hours. I will be having office hours for the next 2 weeks at my regularly scheduled times. All right, so Mondays and Wednesdays from 2:30 to 5, and then Tuesdays and Thursdays from 1 to 5. All right, so feel free to come pick up your graded exams once I let you know that I've completed grading. like I said, I'm going to do my best to finish by class tomorrow, but more realistically, it'll probably be Tuesday morning. So, uh, yeah, so uh, sorry about that. But other than that, hopefully this helps out. And like I said, I'll be in class on Monday if you want to show up to ask questions, right? Hope you're having a great weekend and hope all your classes are doing well, your other classes. All right, I'll talk to you Monday. Thank you.